Hi, I like to use this particular example to further elaborate how to use conventional integration to solve convolution. Now, this is a typical example on solving a circuit system here. Now, we don't need to bother about how the circuit is about. Basically, what we need to do is concerning about this. This is the given impulse response. Okay, we're only concerned about the impulse response, and we are also concerning about the input signal. The input signal is this one, which is a unit step voltage. So in real case, that is just like the signal here. We just turn on the power supply. It starts from 0, then we just turn on something like that, right, all the way. So from 0 volt to 1 volt, something like that. So, and we're going to find how the output response, how the output voltage at these two terminals is. Now, when we are solving this problem from the signal and system perspective, we don't need to bother about that. We're simply concerned about the impulse response, then the input signal. And we also try to understand that, try to recall the output. Basically, in this kind is equal to the input signal, xt, convolved with the impulse response. And that is this. Then when we are going to put it into a convolution, we all know that pretty well. That is from minus infinity to positive infinity. Then we are going to change it into t minus tau x tau d tau. I focus many times. This is the variable. This is the variable. Okay, and now we are going to see how we are going to solve this equation into that. Now, into solving this procedure, we will first figure out what is ht minus tau. This is ht. So the very important thing is we are going to replace all the t by t minus tau. So 1 over RC is the same. E minus t become E minus t minus tau. Then ut become ut minus tau. And this is what it is. Then this is the impulse response. Then the input signal, very interesting, basically is xt, is a unit step. A unit step signal is ut. Mind you that what ut is about. Ut is something like that. That is t. Okay, so we are going, physically it is quite obvious that it means when before the switching on, of course, the voltage is equal to 0. When we start to switch it on, at time is equal to 0, then it start to go to 1. So this is what waveform is about. Then we simply replace this simple concept by putting it into ut. Then we write it into u tau. Now, once when we get this particular equation here, the job is trying to simplify a couple of things, trying to get rid of this thing, which we don't like. Another thing is, we want to get rid of this minus infinitive and positive infinitive, which we find it very difficult to take care. Now, before we are going to get rid of everything, we first try to get rid of u tau. At the same time, try to remind you, that's what I changed this one. So this is going to be u tau. Then u tau, we only have value when tau is equal to 0. Anything tau is less than 1, minus 1 minus 2 is going to be 0. Then in that sense, we should be able to replace this this particular lower limit from minus infinity into 0. By replacing that, then we know that start from 0, 1, so we're going to replace this 1 into 1, then replace this 1 by 0, then we will be able to simplify. Now we will be able to simplify this particular integration in such a way we get rid of 1, we get rid of ut, but we still have the positive infinitive, and we still have another t, something like that. So we are going to sort it out on the next slide. Right, coming back here, once when we have obtained that, we focus on this particular unit step function. That is what I said why it's so important. Now we all know that u minus tau, that is what u minus tau looks like. Okay. Maybe minus 5, something like that. So u minus tau, that means we flipped the u tau into the negative here. So anything here goes from minus infinity to 0. When tau is bigger than 0, it goes to 0. In that sense, we will be able to do a little bit more things. Now, but this time we are going to have u minus tau minus t, that is equal to ut minus tau. Okay, they are the same. Then when we are considering that, that is, we are going to shift the axis here, shift this axis here, because of this minus t into t here. So by doing that, this will give us a waveform of something like that. This is tau, this is 0, this is equal to t. So we are going to see a very interesting thing. It has 1 all the way from minus infinity until when tau equal to t. Anything when tau is bigger than t is all equal to 0. By doing that, we can then replace this one and change this one. That is the reason why we will replace this particular integration, become t integrate from 0 into positive, into this time into t here, simply because that. Then we just copy the whole lot. I just put 1 over RC, the constant here, then become e minus t minus tau over RC d tau here. Then by doing that, we will be doing conventional integration. Then we are going to have, right, 1 over RC e minus t over RC, because t is not a variable. Then integrates from 0 to t e to a power tau over RC d tau. So once when we come to this particular form here, then that becomes the conventional integration. Then we've got the RC here, RC and RC cancel, and this one times this one becomes 1. So we'll get this particular answer. And this is why it's so important. We need to understand what is ut, what is u minus t, what is u minus t minus a, something like that. Okay?